lecture 31 of our series on numerical methods in civil engineering, we are going to talk about fitting polynomial through a number of grid points. In our previous discussion, we know that determining a polynomial q of degree m plus 1 through m through m plus 1 points has a unique solution, and we also obtain an expression for the error term, right. We found out how to find the coefficients. We said that you can find, if you know m plus 1 points, you can always fit an mth order polynomial through these points by solving a system of equations, of size of m plus 1 by m plus 1, right. If you solve that system of equations, you can find out the coefficients, the m plus 1 coefficients, and if you can find out the m plus 1 coefficients, you have your polynomial. But solving that m plus 1 by m plus 1 system every time is of course enormously expensive, right. One needs to fit a polynomial in any reasonable computation many times, right, many thousands of times, many millions of times. So if you have to solve that m plus 1 by m plus 1 system every time, it is not going to be feasible, right. So it turns out that there are simple ways of calculating the coefficients of a polynomial, of an mth order polynomial, if you know the function values at m plus 1 points without having to solve that system of m plus 1 by m plus 1 equations. And probably the best known method is given by Newton's interpolation formula, right. And so we are going to talk about Newton's interpolation formula in somewhat greater detail. But before we do that, we want to talk about something which is known as the divided difference operator, because the Newton's interpolation formula is best, the coefficients are most easily calculated using something known as the divided difference operator, right. So recall, before doing that, let us recall that the solution of the interpolation problem is of the following form. So this is my mth order expansion, this is my mth order polynomial, and that is my error term, right. That is my error term, which I showed last time in considerable detail, is of this form, right, is of this form. So if we denote this term by b of x, it is clear that b of x is bounded when the m plus 1th derivative of f is continuous in this interval, right. Since this involves the m plus 1th derivative, and if the m plus 1th derivative is continuous in that interval, so it has to be bounded, right. Continuous means that the function values cannot become unbounded, it has to grow smoothly, right, it is continuous, right, so it cannot become unbounded. So b of x is bounded in that interval, so that means that the error term is also bounded, right. We now define a new divided difference operator. Now the divided difference operator can have any number of arguments, but the most simple form of the divided difference operator is denoted like this. Divided difference operator of x0 x, right, where it involves a function f, right, is equal to the function evaluated at x minus the function evaluated at x0 divided by x minus x0, right. So this is with just two arguments, but this operator can have any number of arguments, meaning depending on the number of grid points, right. So thus f of x0 x is given by this. Why? Well, let's go back and take a look. F of x is given by this, right. So f of x0 is equal to c0, right. F of x0 is equal to c0. F of x minus f of x0 is therefore c1 x minus x0 c up to cm x minus x0 so on plus this. The c0 term vanishes, right, because f of x0 is equal to c0, right. So that is that. Then I am dividing by x minus x0, so I am left with c1 plus cm x minus x1 up to x minus xm minus 1, fm plus 1 xi m plus 1 x minus x1 x minus xm. So this x minus x0 term vanishes because I am dividing it by x minus x0, right. So I am left with f of x0 is equal to that, right. Now if instead of x I replace x by x1, what do I get? all the terms vanish except the first term, right. So that tells me that f of x0 x1 is equal to C1. So what does this allow me to do? This allows me to express the coefficient C1 of my polynomial, of my mth order polynomial, in terms of the divided difference operator with arguments x0 and x1. So given if I know f of x0 x1, I can find out C1, right. So this allows me to express this coefficient in terms of this divided difference operator. Next, we define in general we define f, the divided difference operator with k plus 1 arguments, the divided difference operator with k plus 1 arguments from x0 up to k plus 2 arguments actually in this case, right. So k plus 2 arguments as this. So f of x0 x1 up to xk minus 1 by x minus f of x0 x1 xk minus 1 xk divided by x minus xk. So we take this as a matter of definition, right. This is how I define the divided difference operator with that many arguments, right. So if I have instead, if I have f of x0 x1 x, what will I have? F of x0 x1 x will be equal to f of x0 x minus f of x0 x1 divided by x minus x1, right. So it will be like that, right. Similarly, f of x0 x1 x2 x would be equal to f of x0 x1 x minus f of x0 x1 x2 divided by x minus x2, right, like that, right. So this is how I am going to define the generic divided difference operator, right. So f of x0 x1 x is going to be this, I just talked about that, right, and f of x0 x we know is this, we have already calculated that to be this, right, and f of x0 x1 is given by that. So again C1 cancels out, right, C1 cancels out, this C1 cancels out that C1, and I am dividing by x minus x1. So I have C2 plus C3 x minus x2 plus Cm x minus x2 up to the and this, right. Again, if I evaluate this at x2, f of instead of x, if I evaluate it at x2, what do I get? Every term vanishes except the first term. So that allows me to write f of x0 x1 x2 is equal to C2. So I can write the second coefficient of my mth order polynomial in terms of the divided difference operator with arguments x0, x1 and x2. Similarly, we can show by induction that f of x0 x1 xk minus 1 x is given by this, right. You can see that this is going to have exactly the same form as this, right, right, and because of this we can write f of x0 x1 x2 xk. So again all the terms will vanish except the first term, and that is going to give me ck, right. So f of x0 x1 x2 xk is equal to ck if k is lesser than or equal to m, which is of course understood, right, because we are interested in an mth order polynomial, right, we are interested in an mth order polynomial. Okay. So if k is equal to m, f of x0 x1 xm x is equal to b of x. So we know that f of x0 x1 x2 xm is equal to cm, that we know, right, from this, right. But if k is equal to m, then x0 x1 xm x is equal to b of x is equal to fm plus 1 xi m plus 1 factorial. That is not so obvious, right. This is obvious, right, because we have shown it by induction, right. In every stage we could write the coefficients in terms of the divided difference operator, in terms of where the highest term in the divided difference operator has the same index as the coefficient, right. We could find that out. But if I have a divided difference operator which is f x0 x1 xm x, right, we are going to show that that is actually equal to my coefficient of my remainder terms, right. Let's go back and take a look at the remainder. our remainder term was like this, right. So, all these coefficients I have been able to express in terms of the divided difference operator, and I am going to show that the coefficient of the remainder is also given by the divided difference operator with x0, x1 up to xm comma x, right. So, that is my coefficient of the remainder term. This can be shown like this in the following manner. From this expression I can write that f of x0, x1, xm minus 1x, right. So, if I have, instead of k I have xm minus k equal to m minus 1, right, then I will have f x0, x1 xm minus 2 x minus f x0, x1 xm minus 2 xm minus 1 divided by x minus xm minus 1, right. So, that is what I have here, right, that is exactly what I have here, right, and this I know is equal to Cm minus 1, because it is x0, xm minus 2 xm minus 1, that is equal to Cm minus 1, that is equal to f x0, xm minus 2 x, and I am dividing by this, right. So, this I know is given by that, right. So, if you look at this expression and I replace k by k minus 1 by m minus 2, right, if I replace k minus 1 by m minus 2, then I get this expression, right, that expression, right, Cm minus 1 plus Cm this minus Cm minus 1. So, Cm minus 1 Cm minus 1 will cancel. I am dividing by x minus x minus 1. So, I am left with Cm plus Bx x minus xm minus xm, right, xm minus 1, that cancels out. So, I am left with this. So, hence f of x0, x1, xm minus 1 xm is equal to Cm. So, here if I replace x by xm, this term vanishes and I am left with Cm, right. So, f x0, xm, xx, this is what we wanted to evaluate. If you go back and take a look, this is what we wanted to evaluate. That is equal to f x0, xm minus 1 x by definition, right. This is how we have defined our divided difference operator, x0, xm minus 1 x minus f x0, xm minus 1 xm by x minus xm, right. Now, we know that this thing x0, xm minus 1 xm is equal to Cm, right. We know that that thing is equal to Cm plus Bx x minus xm, right. This thing is equal to that. So, Cm plus Bx x minus xm, this term minus Cm is equal to give me Bx x minus xm, x minus xm cancels out, I am left with Bx, which is my coefficient of the remainder term, right. So, I have been able to show that the coefficient of my remainder term I can write in terms of the divided difference operator like this. Now, using the fact that the coefficient Ck in terms of divided difference can be written like this, the solution of the general interpolation problem can therefore be written like this. So, everywhere let's go back to our solution of the general interpolation problem, which was like this, right. So, everywhere I am going to replace my coefficients by the appropriate divided difference operator, right. If I do that, I can write it like this: q of x is equal to f0 plus sigma j equal to 1 to m f x0 x1 xj, right. So, if j equal to 1, I will have f x0 x1, right, and this will be from x minus x0. The second term will be j equal to 2, that will be f x0 x1 x2 times x minus x0 into x minus x1, and so on and so forth, right. So, that is the first part of my coefficient of my polynomial expansion, and the remainder then equals, remainder is fx minus qx, which is equal to this, which we already know, right, which is this, which we already know, right. This is the remainder. and that is equal to this term, and this term from here we can write as f of x0 xm x times x minus x0 x minus x1 up to x minus xm, right. So, we get this thing is equal to that thing, right, which we have already, which we actually already showed, right. Is that clear? So, each of the coefficients of the, later on we will show that these coefficients, right, they can be calculated recursively. It is very easy to calculate these coefficients, right, but before we do that, let us talk a little bit more about this. So, each of the coefficients of the polynomial expansion can be expressed in terms of divided differences, Thus, if we can find a way to compute the divided differences easily in a recursive manner, then finding the polynomial qx is a relatively easy task, right. So, given these m plus 1 points, right, and given these m plus 1 function values, it will turn out that I can find out all these coefficients relatively easily using a recursive relationship without having to solve that m plus 1 by m plus 1 equation, right, and we will do that using the divided difference operator. But in order to do this, we have to show something before we do that, and that is we have to show that the divided difference operator f x0 x1 up to xm is a symmetric function of its m plus 1 arguments, where m is an arbitrary natural number. What do I mean by a symmetric function? That means the order in which these x1 xm appear in this divided difference operator is not important. Why? Recall that this is given by this, Cm is given by this, right? But Cm is the leading coefficient of the polynomial Qx, which is the unique solution of the interpolation problem. It is the leading coefficient because it is the coefficient of the largest term, like term of the highest order, right? It is the leading coefficient of the polynomial. However, the solution Qx to the interpolation problem made no assumptions about the ordering of the points where the function values are known. We just said that the function values are known at x0, x1, xm plus 1, right, xm plus 1, xm, right, x0, x1, x2 up to xm, right. We did not say anything about how those points are ordered, whether x1 is greater than x0 or x0 is less than x1. We said nothing about that, right. So, these points can be ordered arbitrarily, right. So long as the function values at those points are known, it does not matter, their order does not matter. So, similarly, their order in the divided difference operator should not matter. Since the solution of the interpolation problem is independent of how the points are numbered, right? I can call a point C1, I can call a point x1, I can call it xm, I can do anything, right? It does not matter. So long at that point, the function value is unique, right? So I can call a point x1, the function value remains the same when I call it at xm, right? That does not matter. The polynomial is not going to change because I change the name of the grid point, right? So I just showed a little picture here. Suppose I fit a polynomial like this, where I initially had the points ordered like this. Now instead of that, if instead of calling this point x0, I call this x3, and instead of calling this x1, I call this x7, nothing changes. I still get the same polynomial, right? I am still going to get the same polynomial because the function value at this point is the same. This function value is the same here, this is the same here, this is the same here. So the ordering, the index by which I refer to those points is not important. Because of that, since the solution of the interpolation problem is therefore independent of how the points are numbered, right, Cm is a symmetric function of the points. That is, whatever the ordering of the points, whatever the numbering of the points, since the function values at the points do not change, Cm does not change, right. So what does this mean for my expression here, for my divide? So Cm is equal to f x0, x1, x2, xm, right, but Cm is also equal to f of x2, x0, x1, xm, right. So, however I order those points in the divided difference operator, my coefficients are not going to change, because what is Cm? Cm is the coefficient of the term with the highest power in my polynomial expansion. My polynomial expansion is unique. That means the term with the coefficient of the term with the highest power is also unique, right. It cannot change, right. It should not change with how I call the points, right. So, is that clear? So that is very important, right. Cm is a symmetric function of the divided difference operators, right. Cm is its coefficients are a symmetric function of a divided difference operators. So, let us recall again that f of x0, x1, xk minus 1, xk x is given by this by definition. Now, let us call the first point xi plus 1 instead of x0, right. I can call it anything so long as the function value at that point does not change, my polynomial is not going to change. Since my polynomial is unique, my coefficients are unique, right. So, instead of calling it x0, I can call it xi plus 1. In that case, what do I have here? I have xi plus 1, I plus 2 and so on up to xk minus 1, xk x, and that is equal to, again instead of 0 I have I plus 1, I plus 2 xk minus 1 x. Here I have again xi plus 1, xi plus 2, xk minus 1 xk, and I am dividing by x minus xk. Then I set x is equal to xi, right, and then I use the symmetric property of the divided difference operator. Because of the symmetric property, f xi plus 1, xi plus 2, xk minus 1, xk x, I have replaced x by xi, I can move the xi right in front, right. I can move this xi right here and I get f of xi plus 1, xk minus 1 xk, right. So, this if I replace x by xi, I have I plus 1, I plus 2, k minus 1 xk xi. Then I use the symmetric property so that I can interchange the arguments any way I like. Interchange, I put xi plus 1 right in front, right. So, xi right in front. So, I have xi plus 1 xk minus 1 xk. Similarly, here, right, I replace x by xi and move the xi right in front, right. So, I have xi plus 1 xk minus 1, right, and this I leave unchanged. Xi plus 1, here there is no x, so I need not replace it with xi. So, I have f xi plus 1 xi plus 2 xk minus 1 xk, right, and then I just interchange this. So, I move this here and I move this there, that gives me a negative sign, right. So, I get xk minus xi. To cancel the negative sign, I interchange the order of these arguments, right. So, I move this here, move this there, and I get that, right. So, now what do I have? I have xi plus 1 xk minus 1 xk is equal to f xi plus 1 xi plus 2 xk minus 1 xk minus this divided by xk minus 1 xk minus xi. It turns out that this is what we need. This yields the recursion formula. Why? Let us take a look. So, we know by definition f of x0 x1 is equal to f of x1 minus f of x0 x1 minus x0. Similarly, f of x1 x2 I know, f of x2 minus f of. So, all these I can evaluate by definition, right. This I know I can. So, if I know the function values at x0, x1 and x2, I can evaluate these divided difference formulas, divided differences, the second order divided differences, right. Now, I am going to use this relationship to evaluate the higher order divided differences. Suppose I want to find out f of x0, x1, x2, right. Suppose I want to find out f of x0, x1, x2. Let me go back and take a look at my recursion formula. So, I have f of x0, x1, x2. So, how am I going to do that? I will have f of x0 up to x1, right, x2, right. So that is k minus 1. So for f of x0 x1 minus f of x1, right, x0 x1 x2, the next term x1 up to x2, right. So I have f of x0 x1 minus f of x1 x2 divided by this thing, divided by that, right, x2 minus x0, right, or is that right? Let's see, x0 minus x2, right, that's x0 minus x2. So what do I get? So I can evaluate f of x0 x1 x2 if I know these terms, and these I already know from definition, right, and then I use my recursion formula to find out the third order divided difference formula, right. Similarly, I can find out f of x1 x2 x3. f of x1 x2 x3, how am I going to get that? So I have x1 x2 x3, so that will be f of x1 x2 minus f of x2 x3 divided by x1 minus x3, right. So that is, or x3 minus x1, right. So that is exactly what I am going to get, right. So now if I know these, f of x0 x1 x2, f of x1 x2 x3, I can find out f of x0 x1 x2 x3. So and remember, my coefficients are c1 is equal to f of x0 x1, c2 is equal to f of x0 x1 x2, c3 is equal to f of x0 x1 x2 x3. So I can find these coefficients really simply by using these divided difference formulas, right. So I do not need to solve my m by m plus 1 by m plus 1 system. I can find out, given any number of points, right, I can find out the highest degree of polynomial. To pass through those points, I can find out the coefficients using this little table, right. And if you code it in a computer, this can be done in a fraction of a second, right, in a fraction of a second. So continuing in the above manner, it is possible to compute all the coefficients Ck, since we know Ck is equal to this, right. Ck is given by that for k lesser than or equal to m, right. So up till this point we have not said anything about how my grid points are located in space, right. It's not necessary from whatever we have done up till now, to assume that those grid points are equally spaced, right. It's not necessary, right. But now if we make a further simplification, if we assume that my grid points are equally spaced, right, that is, if x0 is my initial point, x1 is equal to x0 plus h, x2 is equal to x0 plus 2h, and x3 is equal to x0 plus 3h, xk is equal to x0 plus kh, then it is possible to establish a relation between the divided difference operator and the forward difference operator that we encountered earlier, right. It is possible to do that, right. I haven't shown that, but it can be shown. It can be shown that f of xi plus 1 xi plus j is nothing but the divided by the forward difference operator operating on fi j times, right. So I start with the function value at I, right, and if I operate with that on that with the forward difference operator j times, I divide it by h to the power j by factorial j, then I get my divided difference operator, right. It sort of makes sense, right, because here you can think of it that first time if I have fi, right, I operate on that with the forward difference operator once. What do I get? I get fi plus 1 minus fi. I operate it again, I operate it again, I operate again, I do it j times, I get this thing, right. It can be shown, right. If it is best shown by induction, right. So I would show that it can easily be shown for j equal to 1, right, and then I can show it for j equal to 2, and then I assume that it is true for j equal to k, and then I can show that if it is true for j equal to k, it's always going to be true for k plus 1, right. So that can be proved. So if the points x0, x1, xm plus 1 can be spaced equally apart, then in that case Newton's interpolation formula for the equidistant case can be written like this in terms of my forward difference operator, taking advantage of this equivalence between the forward difference operator and the divided difference operator. I can write my Newton's interpolation formula in this form, right, where it involves the forward difference operator instead of the divided difference operator. Earlier on we showed it for the divided difference operator for the most general case, right, where there was no restriction on how the points were on the x-axis, right. There was no restriction. The intervals could be anything, large, small, equal, unequal, anything. But then we said that if those intervals on the x-axis are equal, then instead of having to use the divided difference operator, you can write your Newton's interpolation formula using the forward difference operator like that, right. And I am going to show that in a relatively simple way, right. So we recall that x minus x0, x minus x1, x minus xj minus 1 can be written like that. Why can it be written like that? Because x is equal to x0 plus ph, right. I just said that x is equal to x0 plus ph, right. Since x is equal to x0 plus ph, x minus x0 is equal to ph, right, ph. X minus x1 is equal to x0 plus ph minus x0 plus ph plus h, right. So that is going to give me p minus 1h and so on and so forth. So this I can write in terms of powers of h. I can bring out all the h's together. I can write it in powers of h to the power j, p times p minus 1 up to p minus j plus 1. And we know that f of x0, let's see, f of x0, x1, xj minus 1 xj, right, that can be written like this. So since I plus 1, I plus j is that, so that is nothing but delta j f0 h to the power j by factorial j, right, delta j f0 h to the power j by factorial j, right. I have just used that formula where I instead of using I have replaced I by 0. I have replaced I by 0, and then I can write f of x0, x1, xj minus 1 xj is equal to delta j f0 hj by factorial j, right. And also recall from earlier that this expression f of x0, x1, xj minus 1 x is equal to fj xi by factorial j. Where did we see? Well, let's go to let's see, I don't remember, but I think let's go back. Right here, right, this is where we showed that, right. So we showed that to be true. We showed that to be true. Now let's go back to Newton's general interpolation formula, that written in terms of the divided difference operator, that is qx is equal to f0 plus sigma j equal to 1. This we have already seen, right, in terms of the divided difference operator. And this, on substituting this here, right, this term with this, right, and this term with that, right, this term with that, and this term with this, we get the desired result, which is equal to that, which shows that in case you have equidistant grid points, you can write Newton's interpolation formula in terms of the forward differences, right. Okay. So, it is clear that fitting a higher degree polynomial of order m requires a knowledge of the function values at a sufficient number of grid points, b computation of the coefficients of the polynomial using divided difference, the recursive form of the divided difference algorithm, or some other recursive algorithm. There are other recursive algorithms as well, but I am just showing one particular one, right. However, even if we use the divided difference operator to compute the coefficients, if we do it several times, if we have to do this over and over again, it is still non-negligible expense, right, because every time we have these many points, the function values to compute it is much cheaper than inverting the matrix, that is for sure, right, but still the cost is non-negligible, right. So somebody might say that, well, let's step back and take a look. So I have m plus 1 points and I have m plus 1 function values, right. Why am I fitting an mth order polynomial at that point? I am fitting an mth order polynomial at that point because I want to find the function value at any arbitrary point in the grid, right. So I have my function values at the grid points, but if I can fit my mth order polynomial through those function values, I can find the value of the function at any point, not necessarily at a grid point, which is not necessarily a grid point, right. That is what I want to do, right. And in order to do that, I am fitting that polynomial, and in order to fit that polynomial, I am having to calculate all these coefficients. And I found out a relatively cheap way to calculate these coefficients. But why? Somebody might say, why do I at all need to fit a polynomial through these points, right? If I know the point, if I have m plus 1 grid points and I want to find the function value at a particular point x which does not lie on the grid, if I can figure out between which two grid points that x lies, why don't I just do a linear interpolation? I know the function values at those two grid points, why don't I fit a line through those grid points, and why don't I get the function value at that point, right? So, well, it turns out that there are advantages as well as disadvantages. It is a lot cheaper, right? Fitting a line through 2 points is much cheaper than fitting a polynomial through mth order polynomial through m plus 1 points, right? But there are problems. Well, an alternative approach might be to use linear interpolation. Suppose we know the function values at x0 through xm, and we are interested in evaluating the function at x, where we know that x lies between xk minus 1 and xk. Then, instead of going through the expense of fitting an mth order polynomial through the points x0 through xm, a simpler solution might be to calculate f of x by linearly interpolating between f of xk and f of xk minus 1, which are function values evaluated at xk and xk minus 1. When is linear interpolation sufficiently accurate, right? That is a question, right? When is linear interpolation going to give me a good estimate? I know that linear interpolation is going to be cheap, but is there any condition which has to be fulfilled for linear interpolation to give me good results? Well, let's see. Suppose we have a table of equidistant correctly rounded function values evaluated up to t decimals. Suppose I have a grid, right, equally spaced grid, and suppose I know the function values at all those grid points up to t decimal places, right, and it is rounded off accurately. It is rounded off accurately up to t decimal places. It can be shown that in a table of equidistant correctly rounded function values, like a table of values, right, m plus 1 values, right, and the function m plus 1 grid points, m plus 1 function values, if the second derivative, if the second forward difference del square f calculated from the function values satisfies this criteria, how am I going to calculate the second difference? Well, I know the x0, x1, x2 up to xm plus xm, right. So I know the function value at 0, f0, f1, f2, fm, right? I know the function values. I'll calculate the first difference, f1 minus f0, f2 minus f1, f3 minus f2, and so on and so forth. That's how I'm going to calculate the first difference. Then I'm going to calculate I'm going to take the difference on that again. So I can generate the second difference, right? And if for a particular table of function values, it turns out that the second difference, that all the second differences are less than 4 into 10 to the power minus t, right? Then the total error in linear interpolation is going to be almost equal to 10 to the power minus t. So what is the criteria? The criteria is that I have a table of function values and then I calculate the second difference, right? And if the absolute magnitude, the largest second difference is less than the precision level of my calculation times 4, right? Precision level of my calculation times 4, then my total error in linear interpolation is almost going to be equal to my precision, right? It is going to be equal to my precision. Even here we can realize that this condition is going to be relatively very hard to fulfill, right? When is the second derivative? I have some function values, right? I have a equally spaced grid. I know the values of the functions at all those grid points. I take the first difference, I take the second difference. When is the second difference going to be really small? The second difference is going to be small when my grid is small, when the variation is relatively large, is relatively small, between when my function doesn't change much, right? When my so if I have very wild variations, then there is no guarantee that this thing is going to be small, right? So either my interval is very small or my function is very well behaved, right? Either of those conditions have to be fulfilled, right? Very well behaved means it is almost very close to a straight line, right? And so both these conditions, if my interval size is very small, automatically my function will become closer to a straight line, right? Or if my function is very well behaved, right? If my function is very well behaved such that these differences become smaller and smaller, right? So ultimately, when is the difference going to be 0? The difference is going to be 0 when I get a straight line, right? The straight line, or when I get a constant, right? The constant, if I get a constant, the difference is going to be 0. So if I start with a function which is a quadratic, if I take the first difference, I am going to get a straight line, right? If I take the second difference, I am going to get a constant, right? So if I start with a straight line, I'll get the first difference, that's going to be a constant. The second difference is probably going to be 0, right? So this, you can see that if the function is very different from a straight line, right, or by interval is sufficiently small so that even if the function is nowhere near linear, in that little region it behaves like a straight line, only then this condition is going to be fulfilled, right? Only then that condition is going to be fulfilled. But let's try to show this. How are we going to show that? Well, I am going to show that by dividing my total interpolation error into 3 parts, right? The first part is the interpolation error due to round off error due to uncertainty in the known function values. So I know the function values at those m+1 points, but I do not know them exactly, right? I know them only up to the precision of my calculations, right? So I know them up to the up to the 10th digit, up to the 10th decimal place, right? So my function values, there is an error due to round off, that is true. Then there is the truncation error. Why is there a truncation error? Because I am approximating my function by a mth order polynomial. If the function is a higher order polynomial, if it's an exponential function, if it's a hyperbolic function, then whatever be my m, right, I am not going to approximate that function exactly, right? So there is always going to be a truncation error, right? There is always going to be a truncation error. And then there are the round off errors which I make during the computations, right? The round off errors which I make during the computations. So these are the three errors, and when we say that if this condition is satisfied, then the error due to linear interpolation will be almost equal to 10 to the power minus t. We are looking at these two errors only. We assume that that error is sufficiently small to be ignored, and what I want to show is that if this condition is satisfied, the sum of this error and this error will be approximately equal to 10 to the power minus t, right. That is, if I use a linear polynomial, this will be about 10 to the power minus, sum of this and this error will be about 10 to the power minus t, right. So denoting the step size, so we are looking at equidistant. Remember, we are now looking at equidistant grid, at an equidistant grid. So, and if we denote the step size in the table as h, we want to linearly interpolate the function value at an intermediate location, say x is equal to x0 plus ph, p goes between 0 and 1, where f of x0 and f of x1 are known. I know that for simplicity I am looking at a point between x0 and x1, it can be anywhere in the grid, right, but I want to find the function value at a point which lies between x0 and x1, and it is at a distance ph from x0, right. From the result, f of x minus qx is equal to that. This we know is true, right. This we have this is the error, right. F of x minus the polynomial approximation to f of x, that is my error. Xi belongs to that interval. For linear interpolation, it is clear that this truncation error, this is the truncation error, f of x minus q of x, mod of that is going to be given by this m plus 1. M is equal to 1 because I am using a linear polynomial. So m plus 1, that is 2f2 xi by factorial 2x minus x0 x minus x1, right. So that is my truncation error. But if we go back several lectures, right, when we first started talking about the forward difference operator, we were able to show that for the forward difference operator, this relationship is true, right, that relationship is true. So I can write that, but okay, so before that I want to get an expression for this term in terms of p and h. So x minus x0 x minus x1 is equal to x0 plus ph minus x0, because x is equal to x0 plus ph minus x0, that's equal to x0 plus eh minus x0 minus h, right. So that is equal to ph into p minus 1h. Therefore the truncation error, after replacing this thing by that thing, right, and replacing that in terms of this, I get that my truncation error is approximately equal to that, which is equal to this times p into 1 minus p by 2. But since p belongs to 0 and 1, why does p belong to 0 and 1? Because it lies between x0 and x1, right. That's why p belongs to 0, 1. We can show that this is a quadratic, right, and the maximum value of this quadratic is 1/4, right. We are interested in finding a bound for this, so we are interested in the maximum value the right hand side can take. The maximum value of p times 1 minus p is 1/4, and it occurs when p is equal to half. Therefore we know that this must always be less than delta square f0 times half into 1 minus half by 2 is equal to 1/4 by 2, that's equal to 1/8. So this is always less than or equal to delta square f0 by 8. But we have said that this is lesser than or equal to that, right. Therefore mod of RT, the truncation error, is lesser than or equal to 4 into 10 to the power minus 8 minus t by 8, that is equal to 10 to the power minus t by 2, right. So this is how we get a bound on the truncation error. Now that we know the truncation error, we want to calculate the error due to round off, right. So we know that for linear interpolation, q of x is equal to f0 plus p f1 minus f0, right. So at x0 plus ph, the function value is going to be f0 plus p f1 minus f0, right, just by linear interpolation. I have f0 here, I have f1 here. So at a point p between 0 and h, right, ph, that has to be equal to f0 plus p times f1 minus f0. So that is equal to 1 minus p times f0 plus p times f1, right. Now, but we know that each of these function values have been evaluated correctly up to the tth decimal place, right. That is what we assumed, right, that each of these function values are evaluated correctly up to the tth decimal place. Therefore, if the error in these function values are denoted as epsilon 0 and epsilon 1, then both epsilon 0 and epsilon 1 must be less than half into 10 to the power minus t, because it has been rounded off after the tth decimal place. So, whatever is the error due to round off must be less than half into 10 to the power minus t, right, since we assume that the function values have been correctly rounded off after the tth decimal place. The round off error due to uncertainty in input data Rx is therefore given by mod of Rx is equal to mod of this, right, mod of the error in this, right. So, 1 minus p times epsilon 0, that is the error in f0, plus p of epsilon 1, right. We know that, right, because that is my function value. The error in the function value will be the error arising out of this and the error arising out of that, right. So, 1 minus p epsilon 0 plus p epsilon 1, which is lesser than or equal to 1 minus p times 10, because that is the bound on epsilon 0, that is the bound on epsilon 1, must be lesser than or equal to 1 minus p times 10 to the power minus t by 2 plus p times 10 to the power minus t by 2, which if I add together I get half into 10 to the power minus t. Now, we saw that the bound on the truncation error was 10 to the power minus t by 2. We have found that the bound on the round off error is also 10 to the power t minus 10 to the power minus t by 2. Therefore, if I add these two bounds, so this must be less than or equal to 10 to the power minus t by 2 plus 10 to the power minus t by 2, which is equal to 10 to the power minus t, right. So, that tells me that if this condition is satisfied, if that condition is satisfied, and I have calculated my function values correctly up to t decimal places, then if I do a linear interpolation, then I can be assured that the error due to linear interpolation will be of the same order as my round off, right, as my round off error, right. But the critical thing is this thing is not going to be satisfied easily unless the interval is really small, right. For an arbitrary function, that thing is not going to be satisfied unless my interval is really small, right. Therefore, what does that mean? That linear interpolation I can do with very good accuracy if the interval over which I am doing the interpolation is very small. If my interpolation is large, I cannot use linear interpolation, which is something probably you long knew by intuition, but well, this is a mathematical proof for that, right. This is a mathematical proof for that. So, this assumes that the other source of error due to the computations, right, due to the computations with f0 f1 is sufficiently small, right. Thus, linear interpolation can be expected to give satisfactory results when this condition is satisfied. However, for this condition to be satisfied, the points x0, x1 through xm must be sufficiently closely spaced, right. They must be over really a small interval. Given a fixed interval, this requires knowledge of function values in a narrowly spaced grid. That means that if my grid has to be really small, right. If I am going to interpolate, right, my grid has to be very narrow. So again, this, if those of you have done finite elements, right? If you think of P refinement versus H refinement, right, where you make the size of the element smaller and you get good accuracy, right, that is H refinement. And then the other way of getting at it is P refinement, you increase the order of the polynomials. So exactly that same thing is based on this idea, right, it is exactly that idea. If I have to get a good result with linear interpolation, then I have to use a really small grid, right. If I do not want to use a really small grid, I have to use a higher order polynomial, I have to use a higher order polynomial fit, right. Thus, for linear interpolation, to give accurate results, many more table values are needed. I have just given an example here, I will stop with that. For instance, if we are considering a function ln x, right, and desire that the total interpolation error not exceed 10 to the power minus 5, right, then linear interpolation would require a total of 450 points, right. On the other hand, if we would like to get the same level of accuracy, if we use quadratic interpolation, then we need only 100 points, right. So that is very important. So we will continue with this discussion in the next lecture. Thank you.